One is just, I mean, they do the same thing. You just sort of treat them differently. One is the continuous long run, which is basically you try to go for very big inserts. So like I was saying, you can get up to 20K inserts. So if you're feeling lucky, you make your library full of 20 KB fragments, you put them in there, and it'll basically be enough time for the machine's runtime to read through once, maybe twice of your read. The other thing is to intentionally use short inserts. So what will happen is that it'll keep reading around and around and around, and what it will give you, as you see down here, is you'll get multiple sequencing runs of that same piece each time the strand and its complement and the strand and its complement. And one of the things that little black box does is it will take all of these and then it will look at each position and decide if there are errors, whether or not which of them is correct, basically by consensus. And then a little bit more sophisticated thing is if it sees that the links are not the same, it'll have to sort of determine where in there it thinks that one of them had an insert where the others didn't. So like I said earlier on, this is, in its sort of basic form, the least accurate. It only has 85% accuracy, which is not a sort of accuracy that we would release the data for any of the other technologies. But through this sort of circular consensus thing, basically through the consensus, the errors are not always going to happen in the same place. PacBio claims that they have a completely random error model, that it has no real biases. Should jump back a bit and say that one of the things about the Illumina technology is that the longer their runs go, the more likely you get an error. If you come to the class that's on Thursday, when I talk about sort of the basic initial quality processing, I'll show you there how, like, towards the end of an Illumina strand, you always get more and more errors and lower quality. That's not the case with PacBio. They have generally a bad quality, I mean 85% accuracy, but it's no different from the beginning until the end. Another thing to note here is that while the polymerase always starts here, the actual sequencing run where they are detecting which base pairs are being incorporated does not start at the same time. They have some sort of internal issues with their chemistry and stuff, where often things have to sort of ramp up, and you're not going to be sequencing until you're here somewhere. So oftentimes, your sort of first and last strand, especially if you're doing that circular consensus thing, will only be partial strands. They're working on trying to get it something they call hot start, where they're trying to get the whole thing so that as soon as the polymerase is initiated, very soon after we'll start sequencing here. That's something that they are sort of working on. Because one of my friends from grad school was working in their sort of reagents department for a while, and apparently the mix of reagents they use is a very complicated mix. They apparently have just been throwing everything they can in there. It's kind of like a fracking mixture. It's got all sorts of weird stuff in there to slow the reaction down or speed the reaction up or make the polymerase more stable. And they're partly working on that to sort of come up with a way so that it will always start sequencing at the beginning. Okay. Here's just a little bit of sort of raw terminology that you might hear if you start working with these. I was often talking about the Illumina things as just having a read. Of course, here in the PacBio case, we have something we call the subread, which is each time it goes across the main part of the sequence, separated by each of the adapter sequences. So, the thing that some of our early people who were working with us when we were trying to start with the PacBio thing is they often got confused by what we meant by a read and a subread, which is just one pass through part of the region that you want to sequence. What else? This is just more of the same, basically showing you that 4 KB read might just be composed of a bunch of 900 base pair reads of total length. Now I haven't really showed you any sort of the same sort of statistics as I did with Illumina, like this is how many reads you're going to have, this is how many gigabases it's going to be. I feel that's not really as good of a way to measure what you're getting with PacBio. Because PacBio is not something that you're just getting a bunch of bulk reads to do the standard sort of sequencing stuff. Like I said, partly because it's lower accuracy, but also because a lot of the applications, you really just care about how long your read is. So this is sort of showing you, and this is actually one of their older chemistries, they've been managing to get this curve to shift a little bit over here. And why this curve is important, this is actually a better curve to be looking at. So you can see here, this is basically your read length. So like I said, you can get really long reads. There's a little bit older data. You can imagine this actually goes out to about 20K, and this curve actually sort of starts bottoming out near the 20K. Sometimes gotten a few up to like 25K. The distribution still extends. Majority of the reads still tend to be down here in the lower region. But what's most important is the actual subreads, because that's your actual unique part of the sequences you're trying to read. And here, this isn't as good in one of their sort of official slides. But some of their newer chemistries, getting up to more this peak of your subread length, been getting more into the 2,000, 3,000 region, even sometimes centering around 4,000. This is good because this is telling you the majority of your reads are about 4,000. And the main reason why you'd want to use PacBio is because they have long reads. So actually getting this histogram of the subreads shifted further and further over is really a better measure of how useful a particular run is for you than the raw number of bases that have been sequenced. I think this is more of the same. This is just a quick sort of way to explain why people like long reads. Of the sort of, like I said, Illumina sort of dominates the market. PacBio has been trying to find its way into a sort of niche area. One of its niche areas is helping in finishing off the sequencing of genomes. So you have a genome, you have several scaffolds. They haven't quite assembled all the scaffolds into a full chromosome. And usually, this is because there are these repeat regions. The shorter sort of Illumina reads are not going to help you bridge repeat regions. Also, like I said, Illumina has some regions that it just doesn't sequence as well. And so even though your reads are less accurate, sort of indicated in these diagrams by these X marks, these are incorrectly read bases. If you have some sort of existing scaffold, you can imagine, and this is what they call their hybrid technology, which is basically saying you should use our technology to get really long reads, then use something cheap like Illumina to produce a lot of short reads. And what you do is you take a bunch of your short reads and you can correct your long reads. So the long reads have been corrected to what you think they are based on the short reads. And this is one way to sort of use the longer read system. The other thing is if you have a bunch of pre-existing scaffolds, so you've used your short reads, you've had high enough coverage that they've formed, you've been able to chain them together into longer contigs, but you might, like in this case of this red region, this might be a repeat area or some other troublesome region, and it doesn't really matter that the PacBio read is not as accurate, so long as it's accurate enough that you can figure out that this part is unique to over here, and this part is unique to over here. You can use it to bridge these two things and figure out how much space is in between them. These other examples are more or less of the same thing. Their other idea is that, and of course PacBio is big on this idea, what you should really do is get lots and lots of their long reads and pay a lot of money, and then once you have enough long reads overlapping each other, you can basically use them in a similar way to error correcting the short reads, just error correct them with each other, sort of a larger scale version of a consensus region. Yeah, that is most of what I have to say about PacBio.